Hi, I'm Tom Ball, and it's my pleasure today to welcome Eric Harpstead from CMU, where he's doing his PhD, and he's interviewing today and tomorrow with Microsoft Research for a postdoc position. We really look forward to hearing about his work on educational game design. Welcome.
Right. Thank you. Right. So, like Tom mentioned, I'm Eric Harpstead. I feel I always have to introduce myself every time I give a talk. Anyway, so today I'm going to talk about some work that I call seeing experience from many angles, educational game design as a data-informed craft, which involves a lot of different kinds of thrusts of research, and I'll sort of get into those as I go. But so for me, educational games are sort of typified by Oregon Trail. I grew up playing Oregon Trail. I actually grew up blocks away from the people that made Oregon Trail, the Minnesota Educational Computing Consortium. But in the years since that time, educational games have sort of blossomed and grown into all these different kinds of domains and fields and interaction paradigms to really make complex topics tangible and accessible to learners of all different kinds. But what remains a challenge in educational game design, while it has become more common and more widespread, it remains difficult to really understand how we can best support the design of compelling games and transformative instructional experiences. So a lot of people do it, but how do we do it well and ideally reliably well? And why is that a challenge? And so to sort of get into why that might be a challenge, I'm from CMU, I can't get away without citing Herb Simon for something. Herb Simon has this famous quote in his discussions on learning science, that learning results from what a student does and thinks, and only what the student does and thinks. The teacher can advance learning only by influencing what the student does to learn. So essentially, as designers of instructional technologies or instructional experiences, we don't cause learning. We build the environment in which learning happens. We build the tools with which learning is constructed. And so you have to sort of view it from that lens. And there's a similar analog in game design theory from the what's called the MDA framework and the mechanics, dynamics, aesthetics framework, that games are designed as this body of mechanics or systems, interactions. And you can think about those as, like, from a board game perspective, it's what's in the box that's shipped to the player. Or from a video game perspective, it's the hard code that's actually running the game. And when a player comes into that situation, they have this dynamic experience. And they get to play with sort of the emergent implications of those mechanics to create a different kind of experience. And that rises to aesthetics, which are things like, that's where you would envision things like fun or enjoyment, but also things like fellowship or abnegation. And that's where I would argue learning also happens. It happens sort of as the thing arising out of this dynamic experience coming out of mechanics that we look at directly. And another implication of this MDA perspective is that players and designers have sort of cross purposes in how they view the product they're either making or playing with. Where designers look and think largely about the systems and the tangible bits, and players care much more about sort of the experience they take away and how it arises out of those systems, and sometimes don't even get down to thinking too deeply about the hard mechanics themselves. And so I say a central challenge of educational game design is anticipating how your design choices from your design perspective are going to affect that player experience and how that might give rise to learning. And so more concretely, the work I'm going to talk about deals with three main thrusts. So the first is providing designers methods for seeing the experiences their games or simulations or environments create. Second one, of exploring methods for evaluating those experiences in terms of the designer's goals and whether or not they seem to be accomplishing what they're looking to do. And third, developing tools to enable designers to play with the implications of experience within their own environments. And so I'm going to talk briefly about a project on each one of these thrusts and how I think they entail sort of this idea of an educational game design as a data-informed craft. So first, seeing experience. So this thrust really tries to answer the question of what does experience look like? What does that dynamic emergent experience actually look like to players? So one easy way of getting at that is simply do a play test, get a game, give it to some kids or to some players, watch them, listen to their reactions, their interpretations, maybe look at how they approach problems. But that, while that gives you really great rich data, it's also sort of focused on usually small scales. So another approach is to take more of an analytic strategy. These may or may not look familiar to some people around here. The one on the left is actually a heat map from Halo 2 developed by some of the people over at User Research. And then on the right is the play tracer system developed at the University of Washington, looking at sort of strategy approaches through game space to a solution. And so there's lots of, and these are just sort of small samples of the much larger space of game analytics strategies and understanding players at scale with data. And what I'm interested in is seeing what I call solution space, which is essentially the space of all possible, or of all functionally distinct ways of solving an in-game level or challenge. And that's important to know because how people approach a problem or how they solve a problem has implications on either the knowledge they have or the knowledge they're acquiring. And from an instructional standpoint, knowing that is important to understand if your instruction is working the way you want it to be, or if it could be potentially designed differently. And so to introduce a more concrete example, just because it's necessary to understand some of what's coming next, I'll introduce the game Rumble Blocks. So Rumble Blocks is an educational physics game developed in collaboration with Carnegie Mellon's Entertainment Technology Center. It's like our game school, if you're not familiar with them. And it's designed to teach basic concepts of balance and stability to kids in grades K through 3. So giving them ways to play with the notions of physics. And so the way the game works is players are trying to build a block tower using a palette of blocks that can cover a series of energy dots to power the alien spaceship so he can fly away. And so they're trying to save the alien off to the side. So that's sort of the narrative purpose. But what this gives players the ability to do is look at sort of what are the implications of my structural design choices as I'm building a tower and playing with the notions of stability. So when they're done, they put the ship on top. And this causes an earthquake and sort of a test of stability of structures. And if the ship stays on top, they succeed and they move on. And that's sort of winning the game. And if the ship falls off the tower, then the alien gets sad and players have to retry and start over. And so what this does is it gives players a sandbox to sort of work with these different notions of what stability means using a metaphor that makes sense to them. So from a design perspective, every game in Rumble Blocks, so this is just one example, every level in Rumble Blocks, and I'll just highlight the energy dots and the goal because it's kind of hard to see on this background. Every level has an intended solution. So when the designers are coming up with it, there's some way to solve the level. They know it's possible in some way. But there's a whole host of other possible solutions the designers might not have thought of because they're not K through 3 kids or because they might have missed some bug or something. And it's important for them to know, what is this space? What does it look like? How common are some of these solutions? Do we like some? Do we not like some? For example, the one in the third one in the top row actually looks kind of reasonable, looks kind of interesting. Some of the ones in the lower right look kind of ridiculous and maybe shouldn't be possible. And it's helpful to know what are these solutions, and particularly what are the solutions that players look for and not, say, an exhaustive search of all possible things people could do in this space. And so this is generally a clustering problem. And so what we're looking to do is create clusters of player solutions based on common properties or approaches of what they do. And so conventional clustering is a readily available thing. Anybody can import scikit or Weka or whatever. But the problem is game states are highly structured and not easily amenable to this kind of clustering approach. And so what we needed was a way to describe game states and make them amenable to clustering. And this is where we developed what we call conceptual feature extraction. I since have come to really hate that name. But the goal was essentially what kinds of concepts exist in the solutions players create. And the way we did this was through a two-dimensional grammar induction process where you take a game state, you discretize it to a grid based on sort of the size of a single square block. And from there, you learn a exhaustive two-dimensional context-free grammar across all the solutions you have. And so this is blocks that can be horizontally adjacent or vertically adjacent, and then pairs and pairs of blocks, and et cetera, until you have a single block symbol. And then there's also extra rules in there that I'm not going to get into for handling negative space recursively. But from there, you can parse the tower, turn it into a feature vector, and then you can start to do conventional clustering. And so to test whether or not this was a good idea, we had some human assistants take 3 levels in the game that are sort of minimally constrained, and so they're likely to have lots of different kinds of ways to be solved. And we had human raters or human assistants cluster a bunch of screenshots of solutions to those levels, and then we had conceptual feature extraction using a g-means algorithm, which is like k-means, but trying to make Gaussian clusters. And then we compared the result groupings against the human assistants using adjusted rand index, which is like Cohen's kappa, but generalized so they don't have to agree on a number of groups.
So what you described in the grammar was spatial, but what I didn't see was any indication of stability.
Right.
In other words, like if it's going straight up, that's much less stable than if it's
Right.
like flat. So why not incorporate that? It seems like considering that's one of your key things in terms of understanding the difference. Why not incorporate that?
So that's a part of the reason why I don't like the conceptual feature name anymore. What we were looking for was sort of looking at them distinctly in how things can be solved, whether or not they're good or bad. So we've looked at, and I'll get to some of this a little later, sort of tangentially, of comparing these patterns to the two measures of stability to see what is good, what is bad. We're mainly looking at trying to map the space, not necessarily judge the space at this point. Okay. So looking at the comparisons between people and the machine, we get ARIs of about 0.42 to 0.51, which is reasonable for a sort of unsupervised strategy like this, but could probably be better. But you can do some interesting things with this data as it is. So here's a graph of, along the x-axis is all the different levels in the game. And on the y-axis is the percentage of solutions submitted to that level that adhered to the envisioned solution, so from like I showed earlier. And you can start to see that things like the tutorial, generally people are doing what we expect them to be doing, and as you go down, it gets much smaller. This isn't actually the order in which the game plays. That would be pretty amazing if this pattern just sort of happened spontaneously. But you can also look at what is the distribution in other solutions. And so you see things like down here where there's a very common solution that's not the one you envisioned. And you can do analysis kind of like this. So CFE was great for doing this kind of analysis, but there's several limitations to it. So the process requires extensive feature engineering, deciding on grammar rules, specifying what kinds of features, the complexity of the negative space thing that I kind of alighted over. And so from a designer's standpoint, it's probably a little too intensive. It's also very brittle, so if you get new data in, so if you're doing like a sort of a constant online analysis of what people are doing in your game, it has to relearn an entirely new grammar when you get new solutions in, because it's not guaranteed to be able to describe new data.
To understand, who actually writes the grammar? Is it the designer?
You write the rules, the types of rules it can learn, and then it learns a grammar.
It learns a grammar from
Yes.
examples?
Yes.
Okay.
And then there's also some structures that just can't be described using a 2D CFG, like this spiral can't be separated on a two-dimensional axis. So we have a couple of solutions like this in our data set, and our solution for it right now is to just simply treat them like they don't exist, which is not ideal. And so all of that was part of our motivation behind developing the trestle algorithm, which is a concept formation algorithm, and this time I actually believe it's something more conceptual than CFE, that models the way humans learn new concepts from structured examples. And so this is designed to address two of the limitations of CFE in that it's incremental. It'll take in new data as it comes in off the wire. And it's designed to take arbitrarily structured JSON data. So rather than having to decide how are we going to describe our states or how are we going to describe the rules that it learns, you can essentially just say JSON export game state, and it'll work with that. You have to make a lot less decisions. And then it builds a conceptual hierarchy by sorting instances locally and updating the hierarchy during sorting. So the way Trestle works is it follows three major phases: partial matching, flattening, and categorization. And so briefly, the instance representation we're talking about here, like I said, is the arbitrarily structured JSON. It can have numerical values and nominal values. It can have component attributes, which are essentially sub-objects or sub-sub-objects, sort of all the way down. And then it can also have relational data, so it's technically a superset of JSON, where these describe the relationship between two components, so saying like block 1 is on block 2, and things like that. And it takes that into account when it's doing the partial matching process. So the first step is partial matching, where it tries to rename objects to maximize the expected number of correct guesses it could have at its root concept. So given a state coming in, for example, this one, if the UFO in previous instances had previously been called component 3 more often than it was component 1, then you'll rename it because it just aligns the structure better. After that, we flatten the instance out. So you essentially take all of the component structure and describe it in equivalent relational terms. And then you proceed through categorization, which is based on the cobweb algorithm from Fisher back in the 80s. And essentially what this is doing is recursively moving an instance down the tree, entertaining things like splitting nodes, merging nodes, creating new nodes, and at each point choosing whichever option maximizes this notion of category utility, which you can think about as the expected number of correct guesses for all attributes of an instance rather than just one. So it's not like a decision tree which is maximizing prediction of one thing. It's trying to balance maximizing its predictions of all things. And so we did a similar analysis of the clustering with Trestle to reduce flat clusters by iteratively splitting nodes, as you could do with any kind of hierarchical clustering algorithm. And so each node that comes out of Trestle is essentially a probability table of features. And you can use things like a Kaké information criterion to maximize a log likelihood penalizing for having too many clusters, essentially, to choose a time to stop splitting. And we can take that flat clustering and compare it to the ones that come out of CFE, and we find, in general, it does as good or slightly better than what the grammar induction version did. But there's also arguably more information in its original hierarchical organization than there is in the flat one that comes out of comparing to CFE. So this is an example of a Trestle tree on that level that I showed earlier. And you can sort of see that among these different groups, if you can kind of see those clusters, their screenshots get a little fuzzy. Among the different groups, there's sort of a relationship among the patterns that you can see. And exploring this hierarchical representation of the solution space is potentially helping you understand what's going on in it.
So just to be, oh, I guess that's what this slide is going to say.
What?
So as a designer, I've designed this level and I think it's good for something. But you might, so I might use this to say, oh, people might be doing these other explorations.
Right.
Here are these other things people might be doing.
Yeah. Yeah, and this is sort of also at more the unsupervised level of what is going on in this space, not judging it
So
yet.
I didn't have to label anything really here.
Not really. This can take sort of an arbitrary output of JSON. It'll go a lot slower if you do it 100% arbitrary, so you can cut out features that never vary and things like that. But you don't have to label much. I mean, you do pass it in like level by level because that's a label that's important, but yeah.
But just to be clear, you're not looking at the dynamics of the game running here.
Not yet, no.
Okay, this is sort of...
Well, sort of, because these solutions are arrived at
oh, yeah.
by going through some dynamics, but it's not dynamic at this stage.
Got it, okay. Thanks.
So just to understand, so you're getting all these solutions, you're using this to basically cluster them.
Mm-hmm.
Saying here's a cluster that we found,
Mm-hmm.
and then you can line that up with what actual labeling, like a human labeling kind of cluster. But the human labeling is pretty arbitrary, right? I mean, whether these two things are like each other or not is kind of a judgment call. So I'm curious, a couple things. I think one is, how much variance was there among the humans in terms of labeling? And the second question is, are there cases where you're finding a cluster with your automation that is like humans would look at and say, there's no way this is a cluster?
Right. So, because I forgot that I'm supposed to be repeating questions. So the question was, what's the level of agreement between people? And then is there anything that we find in the machine that like the humans are like, this is stupid, basically?
Yeah.
I believe the agreement between the humans on the 3 levels was like, it's between 0.7 and 0.8 on average. I don't remember. I can look it up afterwards. It's relatively high for ARI. And then there are times when you look at the process and you sort of look, I think you can see some of these, maybe. Come on. Where, particularly this group over here, where are these really that different, or are these really that, like, should they be more merged or less merged? And so there's some questions of sort of, is it hitting a good level? And some of that happens because this is sort of an incremental order-dependent algorithm, and so there's elements of passing in random sorts of stuff and see what comes out the other end, or like burning in the data multiple times to get a more reasonable structure. And that does happen to some extent, and that's sort of where you see some of the variance in those ARI measures. But so this is the seeing experience thrust. Provides a way for organizing the space of experiences players explore, and this can help guide designers to sort of the portions of the space they might not have been thinking about themselves, or seeing what comes out of it. So the next thrust is sort of, yeah.
Will you talk about any time when you use this with designers and talk about what they thought?
So I won't in the plan.
Can you talk about that?
But I've done some slightly different from that particular viz you saw. But actually taking it and taking those clusters that come out and actually rendering them on a grid of what feedback did the game give on average, and then different metrics of stability, and looking at does this pattern align to what we would expect or not. And then having them use that to come up with what would they change about the game given the patterns they're seeing. I've done some of that sort of preliminarily. And I'd like to do a much better, sort of more formal evaluation of it. I'm kind of more in the piloting stage at that one. But I can point, there's one graph I can point out when I get to it that is part of that. But so this evaluating experience thrust is sort of a now for something completely different, kind of, in that we're looking now here is the player experience working the way I want it to be? And in particular, what I'm going to talk about here is the idea of a learning curve. So in games and in software and in sort of general HCI systems, we have this idea of a learning curve, sort of colloquially, of having a steep learning curve is a really bad thing. It's really hard, or having a shallow learning curve makes things easy. But what does that really mean, and how can we talk about that at sort of a more formal level? And so the field of intelligent tutoring systems has this process called empirical learning curve analysis, which is a technique for comparing hypothesized models of skill against actual player or student data. And so this is good for both evaluating the difficulty and overall pace of learning within an environment. And then mismatches in data and prediction can really help to highlight incorrect assumptions about what skills are in a particular space. And sort of a central concept in this space is what's called a knowledge component model. So knowledge components are a acquired unit of cognitive function that can be inferred from performance on a set of related tasks. So essentially, if you have a knowledge component in your head, you will do good at tasks that require that knowledge component. It's a relatively simple notion. But what knowledge components or KCs are intended for is to be a unifying formalism for things like skill, fact, ontology, schema, production rule, sort of a thing that can capture a bunch of different ways of talking about knowledge and learning. And then a KC model is a mapping between hypothesized KCs and then game tasks or levels. So you could have a model that looks like this. We're down the y-axis, I guess. You could have game tasks. They could be levels. They could be steps in a problem. They could be problems. You can sort of play with different granularities there. And then on the x-axis, you have different KCs that you hypothesize each one of these tasks exercises or requires. And so essentially, this is a big binary matrix, conventionally called a Q matrix in the literature. And you can take this with some real student data, and you can fit the additive factors model, which is possibly the most unhelpfully named regression model ever. But it's a statistical model that is used to evaluate the fit of different KC models to student performance data. And essentially, it's a special form of logistic regression. It's like a elaboration of item response theory, if you're familiar with that at all. And what it does is it encodes 4 general assumptions about learning. First, all students come into a task with different initial levels of ability, which is modeled as a random intercept for student. All KCs have different initial difficulties, so all KCs have a fixed effect intercept for themselves. All KCs are roughly learned at the same rate across students, which is more a simplifying formalism because you get too many parameters otherwise. But so then each KC has a slope of learning. And then crucially, for what we're going to use the model for, KCs can't be unlearned. There's no forgetting in this model. Now, of course, there's forgetting in the world. But what's important here is we make the assumption that in working with a task or a piece of instruction, students are learning something. It might not be the thing we thought they were learning, but we want to assume they are learning. And so what you're trying to do is find a KC model that makes it look like they are learning. And if you relax that constraint and you have a bad KC model, you can sort of get free model fit by allowing things to swing around more. So it's sort of a constraint in there intended to hamstring overfitting. And so what you get out of fitting a model like this is a learning curve that looks something like this, where along the x-axis we have opportunities to practice a KC or skill. So this is essentially any step or level or whatever that leveraged that skill that you did in the order you did them. And then on the y-axis we have a decreasing error rate. So conventionally these curves are all modeled in terms of decreasing error rate. And so here a steep learning curve is a good thing because you're learning faster. and a shallow learning curve is a bad thing. So it's a little bit of a flip. But the red line that you can see is the actual data from the students, averaged across the opportunities without fitting any models. It's lowest smooth for the graph, but it's not actually model fit in any way.
What was the blue line again?
And the blue line, which I hadn't mentioned yet, is the fit from AFM. It's the actual prediction curve of AFM. So a good fitting model, you should expect the blue line to go ideally right on top of the red line or through that sort of pink error channel. Another feature here that is worth pointing out is that confidence interval around the real data is expanding as you go on. And the reason that happens is because both in games and also in people are leaving, and so that's the tail end. So yeah, and so conventionally the way these are actually normally drawn is they don't have the confidence interval, and you just need to sort of be in the know that n is dropping as you go, and I find that really confusing. So this is a much better way to look at it. But so. To demonstrate how I've used this technique in the past, I have to introduce another game. Sorry. This one's called Beanstalk. It's an educational physics game, again, developed in collaboration with ETC. And again, targeting K through 3 kids, but looking more this time at dynamics of a balance beam. And this is based on some early cognitive psych research by Robert Siegler, looking at how kids reason in a balancing task. In particular, in that, if you remember a balance beam, there's sort of the weight on a placement, and then the distance from the fulcrum. And kids at this age, particularly the K1, so the earlier half of this spectrum, have trouble reasoning with those multiple variables at once and how they interact in a space. So the way Beanstalk works is players are playing as either Jack or Jackie, and they're trying to return the teddy bear to the monster in the sky because it fell down. And as they're riding the beanstalk up to the sky, bugs keep falling on their beam and forcing it out of balance. And what they have to do is grow flowers on places to counteract the balance of the bugs. And so if they can balance it, they get to move on, and the beanstalk continues to grow straight. If they can't balance it, or they run out of water, then Jack falls over, and they have to restart. And one thing you might not be able to see is there's actually 4 positions here, 2 of which are open and 2 of which are currently blocked. So we control how much weight you can place and also where you can place it is sort of the constraints of the design space here. So in doing KC modeling in Beanstalk, we iterated through a series of models, which is sort of common practice in this technique. And the first one we start with, which is a pretty common thing to start with, but also sort of meant to be a straw man, is the single KC model. So this is essentially saying there is one knowledge component in this entire game. It is playing Beanstalk, or if you like, balancing beams. And it's actually kind of a really bad assumption. It's like saying someone is good at chess. We like to say it colloquially, but there's actually sort of several thousand, if not million, skills involved in actually playing chess. And so looking at it as a single unit skill is actually not very appropriate. And so what we end up seeing for this KC model, fit to a single KC, is the AFM fit model is essentially at effectively chance and just a flat line. There's basically no learning and not much, and it's sort of flipping a coin difficult. And then the real data is also sort of kicking all over the line, which is a pretty good indication of poor fit.
So I don't understand that. It seems like if people play the game, I mean, this is just saying they learn the game, and if they play the game 100 times, don't they get better?
It's because the model is bad.
It doesn't fit
But
the data.
okay, well, so what is the model again? I guess it just says they learn a thing. I mean, what does it say?
So the model is looking at as they get a chance to practice this sort of global Beanstalk skill.
Yeah.
They should be getting better and better as they go, like sort of completely monotonically, no relationship across, like if there are different kinds of design constraints or different kinds of ways to think about a level, is that there's only one thing that you have to do in this game. Okay. And generally it doesn't work very well. It's like saying math is a skill, when really math is several subcomponent skills, and potentially appropriate at different age levels or grade levels, but at the macro scale, it's generally not very good. So the first elaboration we did of this model was borrowing on that cognitive psych research and looking at whether or not a solution could be arrived at by purely mirroring what was on the other side of the beam, or doing what Siegler called a conflict balance case, which is essentially that either the weights of the distances on either side of the beam weren't exactly the same, but they did bounce anyway. And as you might imagine, the mirroring strategy is easier, so its intercept is much lower, and then you're seeing learning. Whereas the conflict balance case is much more difficult, its intercept is higher. And there's some learning, but again, the real data is sort of kicking around, and this is a pretty good example of that sort of upward kick is a well-known pattern in this kind of analysis. And as you remember, I mentioned this sort of assumes you cannot unlearn. And so if you find in the real data unlearning is happening, it's not that they're forgetting something or getting stupider, it's that they transition into a new KC that you're not treating differently right now. That's generally the assumption that we make in that case. So we elaborated this more into a 6 KC model. I'm not going to dig too much into what all of these are, but essentially we left that same mirror conflict balance split, but then added in a split for how many pegs you have to deal with on each side of the beam, because that just complicates the algebra of the problem. So if you have to add multiple positions and then create multiple positions, or single, et cetera. And so what I want to dig into are these two, which fit terribly. And so this is the conflict balance where there's a single peg that you have to put multiple pegs on the answer side, and then a conflict balance where you have to put multiple pegs on both sides. So that's essentially the hardest thing. To this point, we've been doing what we call rational cognitive task analysis, just kind of thinking about the problem, how do you have to think through it, and how might we introduce new KCs because of that. But for this next step, we're going to do empirical cognitive task analysis, which is looking at, here you have, these are levels of the game. And then the red and green portions are the actual error rates on those levels. So if it's mostly green, it's a very easy level. If it's mostly red, it's a very hard level. And then that blue line going through the middle is the predictions of AFM for all of the attempts on this level. Does that make sense? And so if you see the blue line in the green area, that means this level is much easier than we expected it to be. And if it's in the red area, it's much harder than we expected it to be. And then there's actually like 40 more levels in between. These are just the extremes. But so first we looked at the solutions to some of these levels on the easier side. And here are two examples. Can anybody potentially guess why they're easier than expected? So they can all be solved by a shallow strategy of just putting a single flower in every open position. You don't have to think about the math, you don't have to think about the physics, you just click open spots and you win. And so we found that, well, that's a problem, and essentially built a small detector to go through all of our level designs and find places where this is possible, and retag those levels with what we called a shallow strategy KC.
I'm confused. The flowers.
Just the flowers. Yes.
You get solution for free.
Yeah.
Oh, I see. So you show the ladybugs, and then they just go click on the open spots on the other. And
Yep.
Solve.
Yep.
Okay.
So we built a small script to go through all of our level specifications to find this problem and tag it with the different KC. And this is what we see now. So that CSM curve, it's still a little wavy, but it's generally at least fitting within the margin of error. The CMM curve is just high and flat, which is disappointing, but it's kind of what you'd expect. It is the hardest skill in the game. And then the shallow strategy just stays low and never does show much learning because it's essentially you just get it for free. And there's actually some interesting properties in the CSM one in that we give them like a single stack of bugs, and then they have to put a single one on the other side, but not necessarily only on open spots. And what that does is it actually factors out multiplication in the algebra problem. And so you get, so there's some interesting potential to use this KC earlier in the game to sort of transition kids more into those conflict balance cases, because it is ultimately the only conflict balance KC that actually shows learning, which is a bit disappointing. So essentially we would say, this is interesting, we should use it more often. The CMM, we might need some more instruction either in the classroom or in the game to sort of bridge to those more complex cases. And we should probably cut anything that can be flagged with shallow out of the game. Essentially the conclusion coming out of this process. Yeah.
To understand, these are all sort of unprompted learning in the sense that the students aren't told that there's concepts that they need to understand or that are important that would connect their effort to the concepts. Because typical teaching is you sort of given a concept and then you give it an opportunity to practice it in some sense, right?
So They are not told explicitly about these labels or things related to these labels. There is some instruction in the game, and sort of guiding them towards thinking about certain things. But there were several conditions in this study. So there's like one condition where there wasn't a lot of that direct guidance, and other ones where they did like a scientific inquiry process of here's a beam, here's a situation, predict what's going to happen, let's observe what happened, why do you think that didn't happen, and sort of working through that. So it did kind of vary a bit. But another thing is in doing this sort of process of sort of playing with changing these KC labels is you're sort of walking away from whatever instruction actually was in the game to try and look at can we find evidence for what they seem to actually be learning, irrespective of what the game was communicating to them. Does that make sense?
Yeah, I mean, I think it's an interesting question to think about unsupervised learning. I mean, we train neural nets with unsupervised learning. With humans, I guess they learn
He's
stuff.
a human.
And so there's also in the feedback the game gives, and it's less clear it's less messy in the Beanstalk case, much more in the Rumbleblocks case. I have other research on that I'm not going to talk too much about. Of the feedback the game gives is sort of implicitly communicating some kind of truth, or like some kind of principles, and your goal as a designer is to make sure that the principles it's communicating are the ones you actually want it to be communicating. Does that make sense?
Yeah.
So the shallow, you say you want to get rid of those. Is that because they're just too easy and they don't contribute to the learning, or do they actually interfere with the learning?
So it's actually, you bring up an question again, sorry, was in the shallow one I said I wanted to get rid of them. Is that because they don't contribute to learning or they're too easy? Is that basically?
Too easy,
or they interfere? Sure.
with the learning?
There's actually an interesting point there, and it's a little more nuanced that my advisor, Vincent Nalevin, has some interesting ideas of. I say get rid of them because they're too easy. They don't necessarily interfere with learning. But he said actually you could use them as sort of red herrings. So introduce them early on, and then immediately follow it up with a level where it doesn't work. And sort of use it as like, acknowledge this is a shallow strategy and that it's wrong. And that actually is an interesting concept that you could also do going forward.
The other thing is there's also the, when a kid is playing a game, having success.
Right.
It increases motivation.
Right.
So if it's not harmful, sometimes having some shallow ones could still be beneficial for their.
Yeah, and there's also we haven't been looking too much at sort of those engagement level things here of is the game too hard, too easy, things like that. I actually forget what the base rate success is on Beanstalk. I know for Rumbleblocks it's relatively high, and kids are generally engaged, but I forget. Yeah.
How many kids and how long does it take usually to do a session on your games?
On any of these games?
And did you iterate the game? Because you made some discoveries, you patched some levels. So did you have to also iterate the game?
So Beanstalk hasn't been iterated, at least not based on this data. It's actually transformed into 3 or 4 other games since, but not since this was done. And the number of students, it's somewhere in the range of 150-ish for each of these. All of these things I'm describing are about 150-ish kids in a data set. Rumbleblocks, I have been doing some iteration, and that's sort of getting into my next thing. So I'll talk a bit about that. So to wrap up on evaluating experience, it's looking at ways to consider experience against designer expectations and sort of question those in the context of data. So my next one is playing with experience. And this is sort of the bulk of where my thesis research lives. So essentially, the first 2 thrusts are what's going on in sort of the dynamics or that emergent quality of your game. The second thrust is, now that you see that, do you like it? Is it good? Is it bad? Playing with experience is like, well, what if you changed something? Now is it better? And so this thrust largely centers around what I call replay analysis, which is using in-game replays of players to support very different kinds of analyses. And so these replays are interesting because they make that ephemeral experience something tangible and concrete that can be examined and molded and sort of played with. And in this work, I've created what I call the replay analysis system, which is a system built in the Unity game engine that helps facilitate replay analysis. And there's 2 major components to it. One is a logger for logging when players are playing. And then following up on that is the replay analysis engine, which sort of takes that log, plays it back in the game, and allows this kind of analysis. So the logs I'm taking are a recording of actions situated in game context. This is not an input stream like a click. So in Rumble blocks, it's pickup block at position XY, release block at position XY. And that is a feature engineering thing a designer must do, rather than saying click down, click up. But why that's interesting, we'll get in, why that's important, we'll get a little interesting in a bit. But essentially, each one of these records comes with 4 features: a selection, action, input, which is a common paradigm in intelligent tutoring systems for describing actions, which is essentially the target of an action, effectively the verb, and then the inputs is a list of parameters to that action, and then the state at the time of the action. And this is mainly because I don't want to trust interpolation, because physics engines are messy. And then the replay analysis engine is a system built on top of the normal gameplay engine that reads those logs in and reenacts the session and then allows for various metric calculations, feature abstractions, things like that. And the way that generally works is given a particular record in a log trace, first it assumes the state associated with that action, essentially and then performs the action by providing the inputs to whatever function ran that action, waits for some stopping condition, calculates an interpretation of the state, and then moves to the next record. Effectively how normal replay works. And what's really useful about this is you're in the context of the original game engine with all of the original sort of live code back again. So rather than deciding on a couple metrics, running a study, and having data, if you thought, oh, well, what if we had recorded this other thing? You don't have it then, whereas here you do. And so I've used this process, what I call a sort of retrospective replay analysis on Rumble blocks, to do lots of different kinds of stuff. I'm just going to sort of briefly whirlwind through some of this, but essentially, so the 3 main goals in Rumble blocks are teaching kids that things with wider bases are more stable, things that are symmetrical are more stable, and things with lower centers of mass are more stable. And what's nice for us is those are all calculable metrics, or they have sort of associate calculable metrics. And we can look at, do they perform those metrics better or worse early in the game versus late in the game. We can look at how do we provide feedback in relation to the actual metrics in the engine. Do we like the way that pattern works? This was some of the analysis with designers I was talking about, where on this x-axis we have one of the metrics, and on the y-axis we have what is the general success ratio for a particular cluster of levels. And we've also looked at, of those CFE features, which ones are more indicative of succeeding or failing. And we found an interesting pattern there that one of the strongest things that matters is what you put the spaceship on. Essentially, is it on a wide platform or a skinny platform? And sort of irrespective of the rest of your structure, is it going to topple off the top? And so that's potentially a problem. And so we've done lots of different kinds of analysis. And from there, we have some interesting ideas about what we might want to do next. So for example, with the spaceship problem, what if instead of having the spaceship fall off the tower for success, it just kind of floated there, and it was about capturing the energy dots? It's possibly one way to fix that problem. Another one is that really these metrics are all kind of about single connected rigid bodies, and rather than a bunch of separate blocks. And so what if we glued them all together and had it work that way instead? So we have several different ideas that have come out of this kind of analysis, and we want to know, are they going to be better? And so this is where we introduce what I call projective replay analysis, which is essentially taking the historical replay data and sending it through a changed iteration of the game to understand if this new version is better or worse. And what this does is adds an agent component to the system for handling the ambiguities between that old version and the new version. And I'm exploring 2 different versions of this agent system. One I call literal projective replay, which is just run what you had before, and if you hit an impasse of that action is no longer applicable or something, you just fail. But it's cheap and easy, so why not try it? And the flexible projective replay, which adds a more intelligent agent behind the scenes based on the trestle algorithm I was talking about before, and a planner to understand how to work in new space. So the way that flexible agent works is existing player recordings are used as training demonstrations to an AI agent system that then plays the game. And so the way that training system works is first demonstrated actions. So the recordings from the previous players are explained using an iterative deepening planner and a set of transformation functions to find a general explanation for the action's inputs. So for example, if I were to have placing this block in this position, you could explain that in reference to, say, the x value of this dot and the y value of this square. You could use a function like plus a block, or like a block away from this rectangle for its height, and then also a block away from the center of the rectangle. or you could use, say, in the middle of two things, to describe where did the particular parameters of that action come from. And then from there, the state is paired with game feedback and associated into a Trestle knowledge base to learn a classifier when that action is applicable. And so, so previously I mentioned Trestle was a clustering algorithm. And so here I'm using it for classification. And that seems a little weird. So why am I doing that? So part of the motivation behind, or the evaluation we did when we developed Trestle was, does it actually make decisions in a similar way to people? And so what we did here was this, we took a bunch of mechanical Turkers and gave them a task looking at a picture of a tower in Rumble blocks and saying, is this category 1 or category 2? Where in this case, category 1 is stand and category 2, did it fall? We wanted to do it at this sort of abstract level so that the Turkers would have a sort of a similar level of domain knowledge to the space as the agent would. And then once they made a decision, we told them if it was one or the other, and then went on to another problem. And then we kept doing this for, I think it was either 30 or 20, 30 items. And so this is the results of that, where the blue line are the humans. It's only 20 humans, I think. So we probably could do to have a few more. But then this green line is a decision tree using the conceptual feature extraction grammar rules. And then the red line is Trestle performing this task using just a standard JSON representation and the feedback. And so originally what we had when we first ran this was the decision tree and Trestle, and we were all kind of sad because Trestle sort of gets better and then it gets worse, and it's like, well, that's not great. We would like a machine learning algorithm that just gets better and stays better. But then when we ran humans, we actually found out that humans have this similar kind of reversal effect. We think one of the main reasons for that is sort of the Trestle has a way of sort of indirectly modeling the idea of forgetting by losing a retrieval path to information, because it's sort of constantly restructuring its knowledge base. And humans have a similar kind of pattern where rather than thinking about forgetting as you've deleted knowledge, it's that you no longer remember how to find it, essentially. And you can have a similar kind of pattern explored here. So Trestle makes sense in this classification sense for this agent to understand success based on state. Yeah.
So in terms of number of training items, is this sequentially presented?
Yes.
And so let me just understand. So like in item 11,
Yeah.
very few humans got that one right. Is that correct? Is that the way
Yes.
to interpret this?
Yeah.
So it had to do with actually the difficulty of the problem.
And important to that, so the question was about, is this sequentially presented and the difficulty of the problem? The humans are always seeing a random sort of towers. So some of this is just kind of the noise
So the 11,
that came out of that.
So the item 11 there, it was the 11 thing was always different for the humans, right? You're saying.
I'm not sure I can say it was always different,
But I'm just saying it was random.
but it was random.
So the very low performance is just accidental, that it happened to be that on the 11th thing, it was just hard for everybody. Okay. Yeah.
And really, chance here is like should be here, because it's essentially randomly picking between two
I
labels.
was gonna say, that's a
Yeah.
very low performance if it's randomly, if
Yeah.
the problem's randomly picked.
Yeah. But they do eventually start getting sort of what is the pattern here. And some of that it is kind of a really difficult task to do with zero context of is this 1 or 2? And like what does 1 and 2 mean? What are you trying to have me learn here? But that is roughly equivalent to what the agent is doing. Yeah.
Well, I'm confused. Did you tell them what category 1 and category
No.
2 meant?
No.
Literally, they just
1 or 2.
applying
But then we told them if they were right or not
Yeah.
when they
It's like the game of Mastermind.
basically. Yeah.
Yes.
Yeah.
Spy games.
Okay.
They're modeling what the
Because we wanted to stay abstract because that would be equivalent to what the agent would have.
So, is there any chance that after 11 items, you're modeling fatigue of annoying games, triggers, as opposed to something that can keep their attention for that long?
I hadn't thought about that. It is possible that there's sort of some fatigue element going on.
Like, if you modeled, again, your the error bars on each of these things, just to indicate the confidence interval as people drop off, did everybody last 30 items of the
Yeah.
game?
Yeah. Granted, it's only 20 people. That's one of the issues.
Sure.
I actually do have a version with the error bars, and it's actually like way more compelling than this, but this is slightly more true. I can show you that if you want. It's actually a really great graph.
I'm curious if there's a way to tell
Because when you model with the error bars, essentially the trestle line lines up right through the center of the human data almost perfectly.
But is it saying that they're performing better after 11 items, or like?
Yes.
if it's, well, they're performing worse.
Wait,
The
yes.
errors
So actually 11 was easier. This is error.
yeah.
So 11 happened to be easier for people.
It's
Right.
more of an annoyance effect as opposed to
Right.
a, you know.
Yeah. Cool. Okay.
There is this pattern that it comes down and then, like trestle it does, because it might also have something to do with flow,
Right.
in terms of fatigue.
Mhm.
Would also sort of fit into that, about keeping them in the flow and after a certain point
Yeah.
in time. It's interesting that trestle would have that, like you would expect that an agent would be less susceptible, would not be susceptible to
Right.
things like
Yeah.
fatigue or flow, but, so yeah, I don't know, it's interesting.
Yeah. So the way that the flexible agent works in comparison to the retrospective replay is essentially, given a new game state, does the agent have an applicable action? If it does, perform it. If it doesn't, it's essentially a simple recognized act cycle. Then wait for the stopping condition if the game has feedback. If no, add it to some list for this attempt. And once we do have feedback, we sort of backpropagate that feedback and train the whole attempt at once. Because an issue with this agent is it's only getting feedback at the end of a level and not action by action like it would want. So unfortunately, there's an ongoing evaluation. I don't have a lot of great final data on this yet. I'm actually running my final playtest of Rumble Blocks next Monday. Where what we've done is we've produced several variations of the original Rumble Blocks game. So things like removing the spaceship as a mechanic, gluing the blocks together. One idea was taking the cliff away because it gets in the way of some things. And performing a bunch of different virtual playtests using both literal and flexible agents in those spaces. And then performing a new classroom study using 2 of those variations with real people to see if the conclusions we reach through a virtual playtest result in similar conclusions that we would have done if we'd just done a new playtest with people again. And so I'll be looking at comparing the level of overlap between the solution spaces generated by each system, and then also looking at those alignment measures of do these principles in the game correspond to positive or negative feedback in the way that we would like. And so in playing experience, this gives designers the ability to treat experience like a material and allows for rapid virtual playtesting and regression testing and things like that of new ideas. And so taken together, I view these sort of 3 thrusts as moving towards educational game design as a data-informed craft of helping people see the implications of what they make, think about whether or not those correspond to their goals or their ideas, and then develop ways for players to actually, or for designers to actually play with implications of new choices and designs before actually going and getting new huge playtests of people, sort of as a more rapid iteration loop. So with that, looking at some future work, which I've tried to tailor a little bit around what I might do if I was here. So one thing I'd love to do is start applying some of this stuff to more domains. So a lot of the programming tasks and things like you're working on at the Make Code work have really similar properties to the game spaces I've worked on so far. They're essentially just big creative tasks with complex structure. And everything I've done here is pretty applicable to those. Admittedly, the structure is different. So like grammar is much more formal in something like a program than it is in 2-dimensional blocks world. But other kinds of approaches work. We've done some work trying to fit trestle models with some Alice data. It's messy, but it does actually learn some kind of structure. It was an earlier version of Trestle too, though, so I don't remember what was interesting about that, or what came out of it that could be used. But then also another thing I'm really interested in is how to define knowledge components and do that kind of learning curve analysis in a programming domain. We've done some work on that, where we defined a knowledge component at a token level. So essentially, does this token exist in a like a TA solution? As a correct or incorrect. Extremely messy, fits terribly, but it was a good first shot. And really the harder problem there is what is an opportunity to practice a skill when you're programming. And there's also elements of you're probably exercising multiple skills, or you're probably exercising multiple KCs in sort of the edits you make to a program before you submit it to get some kind of feedback. And so tearing that out is also interesting.
So on a related point, in the Rumble blocks,
Yeah.
is the notion that something's unstable visible to the user if they put, like if I had a block like this and I place like this, would it just
Yeah.
fall down? So there's an element of learning as you go about stability. Was that visible to the machine, the RPA, in the sense that you had a measure of these actions, right? But were some of the actions failed actions where it caused the block couldn't sit in the place it was put?
Yeah, so there are several ways I handle that for the agent in the replayer, but it's a little complicated. Essentially, a failed action to the agent is if essentially an action results in no change. So if it like picks a block up and then drops it and then it falls back where it was before, it's like that was a failed action and it learns that as a failed action. But things like trying to put, like if I take the block and like try to just put it in the ground or something like that. Thankfully, it doesn't do that very much, but I mostly just kind of treat those as that didn't work and move on. There are ways I could handle that much more elegantly or more intelligently. That's another piece of future work that I didn't include in this of there's several impasse points in that process because it's kind of complicated. And right now, my answer to most of those impasses is punt, but there are several ways it could be done better. And so, to your point of the sort of situational feedback of like the towers falling over just because it's a real-time physics engine.
Right.
That's not explicitly captured in the replayer, but it does note, like it does see that the world is different when it's in a new situation. So it'll try to do that.
Yeah, I mean the equivalent would be people having syntax errors
Yeah.
in their code before they submit, right? So if you don't see every one of those and see how they responded to them, then you're not going to really track
Right.
their sort of more fine-grained learning process. Right?
Right. Yeah. So then another piece of future work I'm interested in is sort of lowering the barriers to entry to this kind of analysis and this kind of work. So currently you need to sort of have a lot of research expertise and development expertise to use most of what I've done. And what I'd like to do is develop methods for working with games or instructional environments so that somebody like just a standard teacher or a standard instructional designer could actually employ some of these things as they're built in more to a tool than what I've done so far. And so this is sort of some of that work I was talking about with the designers of how do they think about this? How would they like to think about this? Is this actually fitting a need that they have, or is this something completely stupid? And looking more into that is definitely a thing I'm also interested in. So with that, acknowledgements to my mentors, my various collaborators. Most of this was funded by DARPA and also the peer program at CMU. And with that, I'll take questions, though I've kind of already taken a bunch.
Can you go back to slide 55, please?
55.
So those three column charts
Yeah.
up top, the symmetry angle, is that saying that the performance or understanding of symmetry was worse after the game was played?
The symmetry angle on average was lower, which is a good thing. Sorry, so the symmetry, it helps if I actually dig into these more. So there's three metrics we're using. Wide base is just the width of the aggregate base of the tower. Center of mass is the height of where the aggregate center of mass is off the ground. Symmetry angle is a complicated way of measuring symmetry of taking a ray from the center of base through the center of mass, and its absolute difference from 90. Make sense?
So
you're saying lower is better.
So lower is better.
There, but in the other two cases, higher is better.
Lower is better is actually in both of these two,
Oh,
and
okay.
higher is better is base. So center of mass, not doing very well.
Okay.
Trending wrong, but also not significant.
more perpendicular,
Right.
Got it. Okay.
So you're teaching physical concept. Have you thought about comparing with teaching with actual physical blocks?
Yeah, so there's a bunch of work by Nezra Yanir at CMU. So she was also sort of part of this work originally. And she's gone and done a lot of physical stuff, and also, interestingly, detecting them with connects and things like that, of trying to do some of these predictions with towers that kids just build out of Legos, and letting them go through a process before the table's actually shaped. And she actually just recently defended her thesis, so there's a bunch of stuff on that in comparison to this. General takeaway, physical is way better, but it's also sort of physically constrained. Yeah.
How many of the games that you talked about in your talk today were built for the purpose of actually teaching kids versus for your dissertation?
So the games were built primarily for the purpose of teaching kids. That's what the Engage project, you might have seen the badge show up every so often, was a collaboration between CMU's Entertainment Technology Center and then us at the HCII, where student teams at the ETC would build these games for purposes of essentially STEM and physics for that K through 3 range, which is why they all have the same grade range. And then we would do the analysis and evaluation and also guidance on sort of pedagogical design. And I would say that process was potentially more swung to their side of the design and development in the Rumbleblocks case. So the Rumbleblocks is much more driven by their side of the equation. Beanstalk was a little more driven by our side of the equation, which is why it's more based on cognitive processes and cognitive research. But their original intended goal was teaching. And I've sort of co-opted them because I'm sitting on the pile of data from all of them and I can use that. So.
How well do these approaches scale? Because one of the things with the types of games you're doing and the age level that you're focusing at is you can reduce it down to a fairly finite problem. What happens when you get things with lots of variables or lots of knowledge concepts? As the complexity increases, what's your thought and how well these approaches scale?
Sure. So the question is, how well do these approaches scale? Particularly when sort of things like you get more concepts and more knowledge components and things like that. So the knowledge component one, the empirical learning curve analysis thing, that's actually been done by, so that's kind of like a bread and butter piece of the educational data mining community. And that can scale sort of lots of different ways. But usually because it's working in well-structured curricula where you have like lessons, you have problems and lessons and units, and you can sort of leverage the fact that each individual modeling problem isn't necessarily the full enormous set. But if you did have a place like that, it's honestly probably more a challenge of what do we think these knowledge components are? Do we believe that they make cognitive sense if you're dealing with enormous data? There's also a lot of approaches for learning knowledge component models, sort of unsupervised way. And those, I think, are the places where you start running into some scale issues of, we learned this model, but what does the model mean? But in terms of actually doing the fitting and looking at the comparison, it's mostly a grunt work problem at that point, but it does reasonably scale. In terms of trestle, that's a thing that I think we actually don't have as great an intuition about as to how well something like trestle scales. I mean, it'll take sort of arbitrarily giant states and arbitrarily giant sets of data, but a thing that I would really like to do potentially a little more rigorously in evaluating the algorithm is understanding how certain relationships between features kind of affects things. And can you bias its processes by how data is encoded when you feed it in? Ideally, it wouldn't be, but it probably is in some ways that are maybe not as obvious on the tin.
More questions? All right, thanks again.